Frame analysis. Video 14. Concrete design according to first order theory, part 2. Under the third tab, calculation settings, where various conditions influencing the calculation are specified. Should compression reinforcement be permitted, and should account for the minimum bending reinforcement demand be taken. In the code, there is also a special condition regarding monolithic construction that can be activated. The program contains a highly advanced non-linear calculation engine considering stiffness changes due to cracking of the concrete, and this means of course an iterative calculation. The criteria of this, the convergence condition, and the number of allowed iterations can be altered in this window. Designing for shear can be performed with and without shear reinforcement. When the calculation is done with respect to shear reinforcement, it is important how the value cotangent theta is chosen. Theta is the angle between the compressed concrete struts and the beam axis in the imaginary truss model, and the cotangent theta value will range between 1 and 2.5. By default, the value 2.5 is used, which gives a minimum amount of reinforcement, but of course it is up to the user to choose the most suitable value. If the calculation is performed without shear reinforcement, it is possible to activate increased shear strength near supports. The code EC2 contains 3 methods to design concrete structures with respect to flexural buckling: the general method, and the simplified methods, the stiffness method and the curvature method. At the stiffness method, an approximate second-order moment is calculated with regard to the stiffness, and at the curvature method with regard to the curvature. The general method requires an analysis according to second-order theory, and the decreased stiffness due to cracking has to be considered. This is the method used when checking the capacity in the frame plane with second-order theory. Out of the plane, the stiffness method or the curvature method is used depending on the user's choice, where the stiffness method is default. If only a first-order analysis is made, like in this case, one of these 2 methods will be chosen for the buckling check in both directions. The next option is called reinforcement, and as mentioned earlier, this is where the bending and the shear reinforcement is defined. With the option long-term parameters, creep and shrinkage are specified for serviceability load cases. To be able to design for buckling, consideration to creep is also required for ultimate load cases, but in that case it is the effective creep value that should be used. We choose the creep factor 3 for the serviceability load cases and the effective creep value 1.6 for the ultimate load cases. Finally, there is also the opportunity to save time by copying reinforcement from one member to one or several others. We now choose Calculate to get the initial reinforcement calculated. When this is done, information about the section forces used to calculate this reinforcement is displayed. We now want to investigate the reinforcement selected, and we then again choose Concrete Input. We look at the first member, 1, and select Reinforcement. We see that bending reinforcement chosen is 16 bars at one edge and 13 on the other. The shear reinforcement chosen is stirrups with diameter 8, cc 245 along the entire column. For the beam member 2, we get 26 bars at the bottom edge, and the stirrup reinforcement divided into 5 areas with different cc distances. We will soon check if this reinforcement is sufficient or not.